Hemodynamic monitoring, we know, is a critical component of caring for critically ill patients. An early goal-directed therapy that incorporates optimization of cardiac output to assist in guiding therapeutic decision-making requires a measured cardiac output that is reliable and accurate. Now, preferably the cardiac output measurement should be available continuously to rapidly detect hemodynamic changes. The complex and challenging nature of our patients requiring our MCS devices is well known. Now, monitoring patient response to selected MCS devices is critical in determining efficacy, adequacy, and appropriateness of the selected device. This discussion will focus on the development of a novel method for calculating stroke volume and cardiac output from aortic flow, which is obtained from a high-fidelity aortic arterial pressure signal. Sorry about that. I will be reviewing the proof of concept of the algorithm and the test results from patient data in a variety of conditions. Now, yes, full disclosure, I am a Teleflex employee. However, this is not about our products today currently on market. This talk is about preclinical work that is a distance from application in clinical settings. And while this work was done in collaboration with physicians and scientists, there are no clinical implications at this time. Early monitoring of patients on MCS therapy, especially the balloon pump, is critical to determine if the device is adequate to support the patient. In many cases, the patient may not have advanced monitoring devices available, and many decisions are made solely on blood pressure or other indirect measures of LV performance, such as cardiac output. When available, cardiac output is the most commonly used measure of LV performance and the basis of many treatment decisions. Having this information from the start of therapy automatically would enhance clinical decision-making. Now, certain balloon pump systems currently calculate aortic flow, which is based on stroke volume from a high-fidelity arterial pressure signal. Information from the flow is used in the time domain to set inflation timing on an intra-beat basis. However, if flow can be calibrated for volume, it would indicate the stroke volume on a beat-to-beat basis. Now, working again with several leading scientists and physicians, we developed a method to calibrate the flow wave for volume and confirmed that even in the presence of the balloon pump, it can calculate stroke volume from the native left ventricle, providing a measure of hemodynamic impact from the balloon pump. Now, there are currently two accepted methods for cardiac output calculations, and thermodilution and pulse contour analysis. The most commonly used is thermodilution method using the Stewart-Hamilton equation. This method calculates the volume that occurs to change the temperature in the blood at 2 points along a catheter. Now, this method can be done by either an injection method or a continuous catheter-based method and is considered the gold standard for cardiac output measurement. It is important to note that the accepted accuracy range on thermodilution is plus minus 15%. Now, more recently, several companies have developed a method using pulse contour analysis. In this method, the area under the systolic component of the arterial pressure waveform is measured and converted to volume. However, in the presence of MCS devices, specifically the balloon pump, the pulse contour method has been shown to be inaccurate because it adds volume displaced during augmentation to the stroke volume. While this can indicate an improvement in systemic perfusion, it does not specifically inform the clinician about LV performance. Now, investigations with FlowTrack from Edwards Life Sciences and Pico Systems out of Germany, those have indicated that continuous cardiac output measurements using pulse wave analysis becomes unreliable in the presence of a balloon pump. The method developed based on the aortic flow wave algorithm addresses this issue. Now, in order to obtain the aortic flow wave, a high-fidelity arterial pressure waveform was used with the three elements of the Windkessel model being applied. Essentially, the process was worked backwards by applying the three factors affecting the arterial system: impedance, compliance, and resistance. Now, the algorithm converts the measured arterial pressure to flow within the beat as the beat occurs. And since peak flow always precedes peak pressure and the downslope or reduction in flow always precedes the reduction in pressure, we can use that time difference to determine the position of the aortic valve closure or the dicrotic notch. Now, this is still only showing the work in the time domain. Now, when calibrating the flow wave to volume, there are situations that can cause an abnormality in the waveform, and counterpulsation or phasic support, most commonly from a balloon pump, causes such abnormalities. However, other devices could also impact the waveform's morphology. In evaluating counterpulsation impact, though, a novel method has been developed to calibrate the flow wave for volume using the arterial pressure and to remove the inflation impact or augmentation from the volume calculation. In the left graph above, a non-assisted arterial pressure waveform and associated flow wave are shown. This information is used to determine the start and end of the systolic portion of the waveform. Now, on the flow wave, the aortic valve closure point to the stable or flat portion of the flow is also determined. The information is used to determine the relationship between pressure and volume. In the right graphs above, during the assisted beat, the position of the aortic valve closure is used to fit a line in red, if you can see that red up there, it's pretty fine, between the aortic valve closure and the end of diastole or lowest point on the AP. This iteration removes the augmentation pressure from being added as volume from the left ventricle. The flow wave fit from the unassisted beat is applied to aortic valve closure to essentially zero the flow and remove it from the calculation of volume. Now, these iterations are run multiple times to get to the baseline and then continuously on a beat-to-beat basis to allow the calculation of stroke volume and cardiac output. Now, this is an example of an early version of the algorithm's performance, and the top graph there shows the assisted arterial pressure waveform in a 1-to-2, something we're all used to looking at. And it is important to note that if you can see the colors, the red and the blue markers accurately detect the start and end of the systolic component of the beat, with red obviously noting the aortic valve opening and then blue the aortic valve closure. This step is critical to ensure only volume from the left ventricle is used for the calculation of stroke volume. Only the area between the red and the blue markers is included. The second graph, the middle one there, shows measured stroke volume from the conductance catheter, which is placed in the LV against the calculated stroke volume from the algorithm. The plus sign indicates the measured volume, and the circle is the calculated volume. In the early version of the algorithm, the comparison indicated good ability to follow the change in stroke volume, but the separation, reduction, and accuracy of the stroke volume measurement. Now, further iterations, further runnings of that algorithm did reduce this difference between the two. The third graph shows the left ventricular volume change measured by the conductance catheter. The red marker indicates the beginning of systolic ejection, and the blue marker at the end of systolic ejection. Remember again, LV volume is inverse of aortic pressure. So this measurement is used to determine the measured stroke volume for comparison to the stroke volume calculated by the algorithm. Now, this slide shows the performance of the current algorithm during Vena Caval occlusion, and this produces obviously a very large change in stroke volume. The top graph on the left shows the arterial pressure waveform and assisted 1-to-2 with the beginning and end of the systolic component of the waveform marked. And you can see the reduced pressure at the end of the trace after that occlusion. The second graph is left ventricular volume, again measured from the conductance catheter, showing the reduction in stroke volume at the end of the trace. And the third graph shows the measured stroke volume, plus sign, and calculated stroke volume with the circle, and you can see that the updated algorithm, completing further iterations for each beat, shows the stroke volume is much closer to the measured volume and correctly follows the change in stroke volume. Calculated precision here of the algorithm is 4.3%. The upper right box shows the data for each individual patient data that we used, and the line represents the mean stroke volume, and the data points closely follow the line for each patient. The Bland-Altman analysis shows the level of agreement of the calculated stroke volume is within plus minus 5 milliliters of the measured stroke volume. Most importantly, the ability of the algorithm to follow the change in the stroke volume is confirmed with a high precision or accuracy. Now, here's our favorite kind of patient on a balloon pump. You have those arrhythmic patients, and this is going to show the performance of the current algorithm during significant arrhythmia. And we all recognize again that arrhythmias can produce significant variations in stroke volume from beat to beat. The top graph shows the assisted arterial pressure waveform in a 1-to-1 assist with the beginning and end of systole, again, component waveform marked as before, and you can see the reduced pressure at the end of the trace. Second graph again is measured stroke volume, compared to our calculated stroke volume, and you can see that the updated algorithm for stroke volume is much closer to the measured volume and correctly follows the change in the stroke volume on a beat-to-beat basis. Calculated precision here is 7.6%. The upper right box shows the data for each individual patient, and you can see that the data points follow closely along the line for each patient. Bland-Altman shows that the level of agreement of the calculated stroke volume is within +8 mLs and -5 mLs of the measured stroke volume. The ability of the algorithm is clear to see that we can follow the change in stroke volume, confirming even in the presence of beat-to-beat stroke volume changes such as an arrhythmia. Now, in the worst case of stroke volume changes, this is really showing us the final example here is from the balloon pump going off to on from a single patient. So this is just one patient data. This event produces the most dramatic and abrupt change in stroke volume over the shortest time for patients. Now, the top graph shows the arterial pressure waveform when therapy is initiated. Again, the beginning and end of systolic component of the waveform is marked, and you can see the reduced pressure at the end of the trace after the balloon pump has been initiated. That's our goal. The second graph is left ventricular volume measured by conductance catheter, and again, you can see those changes there in stroke volume. And the third shows measured compared to calculated. You can see that the updated algorithm stroke volume is much closer to the measured volume and correctly follows the change in stroke volume. However, for a few of these beats, as the pumping is initiated, the separation of the data is visible. Now, calculated precision or accuracy is 11.2% during the change, so initiation of therapy, but does return to 4% after the stroke volume is stable. This is the highest degree of inaccuracy seen, which is still within the accepted performance of thermodilution cardiac output at plus and minus 15%. The upper right box shows the data for this individual patient, and the line represents the mean stroke volume, and the data points obviously follow along closely. Bland-Altman analysis shows that the level of agreement between the calculated stroke volume and measured is plus 11 to minus 10 cc's. This is the widest range of the level of agreement of all cases. Now, these are graphs showing the performance of the stroke volume calculation in a balloon pump as compared to the computer program that the algorithm was developed in. The performance of the algorithm in the pump is virtually the same as the algorithm as it was originally developed. These graphs confirm that the pump is able to calculate and follow the stroke volume changes. This graph shows us from pump off to pump on, again, the worst case scenario for accuracy, comparing the algorithm's performance in the balloon pump as compared to the original computer algorithm. Again, this confirms that the balloon pump algorithm is implemented correctly and working as well as the original. So in conclusion, the ability to accurately calculate stroke volume and cardiac output from the arterial pressure during balloon pump therapy without any additional equipment introduces an important conceptual tool for clinicians to determine if the balloon pump is the right therapy for a given patient and to determine if it is meeting the goals of therapy. The first paper on the performance of this algorithm was published in 2021 and confirms the accuracy range for 4 to 11% with an average of 7% and the ability to follow the changes in stroke volume even during balloon pump support. This is well within the accepted accuracy of thermodilution cardiac output. With new tools such as stroke volume cardiac output calculation shown by this method, clinicians will be able to determine the best course of therapy for a specific patient and see the impact of therapy decisions from the start of therapy. We believe that this will help clinicians provide the best patient care possible and make decisions based on available data. Thank you.
Thank you, Kacey.
Yep.
James Filipich asks, can this new technology be retrofitted to current equipment?
We are not at that stage yet, so we are still just in that development stage. This is all preclinical, so that will be developed and decided down the road. So I don't have a solid answer for that right now. I wish I did. Okay, thank you.
Okay, thank you, Kacey. Our next section is Coming Together Right Now, Over You. This is for all of our companies to be able to tell you where they are right now, where they're looking to go, any new products that are coming up. For those of you that are in the audience, you're able to see all of this, or at least things that are FDA approved, out on the floor. For all of you at home, this is really for you to be able to experience the manufacturers without actually being here in person. So our first is Eva Casamento from Humanetics Corporation. Eva? Thank you.
Good afternoon. I'm